Across Europe, drones are increasingly present in fields, forests, and rural communities, but their real impact depends on how innovation connects with real needs on the ground. The Icaerus podcast series explores how this connection is built through research, use cases, and collaboration with innovators and end users across Europe. To better understand the potential of drones to solve these real life challenges, the project launched an extensive open call to fund 20 smaller projects in two distinct categories. The push calls invited technology driven proposals um, from drone manufacturers, research teams, and SMEs to develop and test new ideas, tools, and prototypes based on drone activities and drone technologies. The pull open calls focused on real needs identified by end users in agriculture, forestry, and rural communities, encouraging solutions that respond directly to concrete operational and societal challenges. Today, we will be talking with a project leader from the push open call and the pull open call. I am Dimitra Furkalidou from reframe.food, and in this episode, I am joined by Sébastien Lambot from GPRSense, one of the teams that were selected through the Icaerus open calls. Sébastien, to start us off, could you tell us a bit more about yourself?
Yes, so I'm Sébastien Lambot. I'm professor and FNRS research director at the Université catholique de Louvain in Belgium, and I'm specialized in ground penetrating radar and hydrogeophysics, including applications with drones. And in parallel, I run a small company called Sensar Consulting, where I do develop GPRSense.
Viewers and listeners who may not be familiar with the project yet, what exactly is GPRSense and how would you explain it in simple terms?
Yes, so in simple terms, GPRSense is a geophysical instrument that lets robots, drones, tractors, or quad, for instance, to measure soil moisture underground, so without touching the soil. So it is based on radar technology that transmits electromagnetic waves into the ground, and then there is a major reflection at the soil surface. And the amplitude of that reflection increases with permittivity and therefore with soil moisture. So the echo, so the reflection that is measured, is analyzed by the software within GPRSense to retrieve that soil moisture. So GPRSense integrates at the same time the hardware, so the radar system, GPS for positioning, and so on, and a fully dedicated software involving advanced radar modeling and calibration of the instruments. So I do have two GPRSense model actually, a low and high frequency model. The low frequency model is mainly dedicated to the root zone moisture mapping, for instance, to support irrigation, while for the high frequency system, it is for shallower applications and high resolution subsurface imaging, like for road inspection, landmine detection, or even satellite products calibration.
GPRSense generates real-time soil moisture maps using full-wave radar inversion. Can you walk us through how radar data actually is transformed into actionable maps for precision agriculture?
Yes, so the first step is that the radar is fully calibrated, including to account basically how it transmits and receives electromagnetic waves, accounting for radar medium, so radar soil interactions actually, including like with drone applications, radar drone interaction. So there is really a full calibration to start with. Then once a measurement is performed, so there is a complete electromagnetic model, so that can describe really the radar signal, which is fitted to the measurement, so to the recorded data. And this is by adjusting the model parameters, which are in this case, for instance, the radar height above the ground and the soil surface permittivity. So once we find through that adjustment the optimal permittivity of the ground, it is transformed into soil moisture using a simple petrophysical relationship that is just an analytical equation. And so if we know the field capacity, either a value or if we map it during very wet conditions after precipitations, for instance, then GPRSense can calculate an irrigation map that can be provided to support irrigation. And so in GPRSense, all of that is automated, so the farmer or the robot does not see directly the radar data, they directly see the soil moisture information. Nevertheless, this instrument GPRSense is also dedicated to science, so the radar data are also available to scientists or developers, for instance.
So now let's talk a little bit more about the GPRSense LF model, which is mounted on drones, and the Oscar irrigation robot for autonomous soil sensing. How does the system adapt its data collection and decision making for such different platforms?
Yes, so for the drone platform, to start with, GPRSense is simply fixed mechanically on the drone, and the user will interact separately with the drone and the radar. So the integration is just purely mechanical. And then the user will plan an automated flight to follow and map like the soil moisture in the field with a regular grid. And the processing can be performed of the GPRSense data either in real time or in post-processing. And then the map can be transformed into like an irrigation map. When GPRSense is mounted on the Oscar irrigation robot, the integration is going deeper because basically GPRSense will be controlled directly by the robot, for instance, to start the system, to start and stop the measurements. And in real time, the radar will stream the soil moisture data to the robot, which can then calculate the irrigation quantity and apply it on the fly. So really, in real time, based on the measurements, directly applying the optimal quantity of water. And so in the upcoming season, so in 2026, we plan to make this full integration with the new version of the Oscar irrigation robot together with the new version of GPRSense. And so we will use that integration and apply it for a complete season of irrigation operation. So to synthesize, so with the drone, usually we map first and decide later based on the obtained map, while with the robot sensing, we can have a real-time application and estimate of the soil moisture to calculate and apply the good quantity of water.
Sebastian, let's hope the best for 2026 and the plan to make this full integration with a new version of the robot.
Thank you.
What were the biggest technical or operational obstacles that you have faced until now, and how did you actually overcome this?
Yes, so with the development of GPRSense, there have been a lot of challenges, I would say, but there have been like three major challenges that I can explain here. So GPRSense mechanical components are made using 3D printing, which is really a great asset, especially during development or even early commercialization, because we can rapidly design the components, print them, and then we have them on the fly. We can also adapt to new designs if needed. But finding the right plastic and the right printing settings was actually very time consuming, because this results from trade-offs between different parameters like the aesthetics, the mechanical robustness, the ease of printing, because the best plastic usually are not easy to print, especially for large components. I also accounted for the toxicity of the fuels that are emitted, and also, of course, for this agricultural application, the resistance to weather and UV from the sun. And so within the Icaerus project, we could reach stable settings for the first version of GPRSense, so version 1.0.0, and also the first sale last year. And over the last 2 months, actually, I found a little bit by chance, I would say, a variant of that chosen plastic that led actually to version 1.1 of GPRSense. And that plastic seems really to be perfect choice. I would say it is much stronger than the previous one. Even the aesthetics is improved, and also in terms of printing settings, now it's really highly repeatable for the printability. So this is one thing about 3D printing, which is really a field by itself. Then also GPRSense integrates various electronic components that are available on the market. And in particular, the battery model that I found, which was really suitable, actually has been in the meanwhile updated by the manufacturer. And the new version do not fit my need for GPRSense. So this was really, let's say, an issue. And so to find a solution to that, I tested several alternatives. And actually, I found one that works very well with a nice electronic logics behind the battery. And so this forced me to completely redesign the internal layout of the enclosure. So this was like a major change, changing the battery. But in the end, actually, that was something good because the electronics became simpler and the manufacturing of GPRSense became much easier. So that's something good at the end. But to avoid and mitigate that in the future, what I'm doing now is that now that I have this good battery, I'm really progressively building a stock of critical components for GPRSense. And finally, during the project, another important obstacle that I faced was the stability of the radar calibration with respect to change of temperature in the field. And during the project, I solved that by basically designing and implementing a new temperature-dependent calibration model. So this was really three major challenges faced during the project and also just afterwards.
It is very important to find out what is not working and find new ways to do it. So this is great what you mentioned. And thank you very much, especially for the engaging example about the battery model. So now to move on, I would like to ask you, across all the test sites, what were the most surprising insights from deploying GPRSense, and how do these results advance Icaerus goals for sustainable, drone-compatible agriculture?
Yes, so actually, when we applied GPRSense in the field, we observed root zone soil moisture patterns, but these were not actually surprising by themselves, also because I have quite experience in mapping soil moisture, but actually these patterns showing relatively high and inherent variability of soil moisture across agricultural fields really demonstrates further that the root zone moisture is highly variable. And so accounting for this variability in irrigation operations can thereby, of course, save really a lot of water and also improve productivity. For example, we observed more than 30% water savings in earlier tests that we did with Osiris Agriculture in the previous European Agro-Food project. So such high-resolution root zone maps actually were not simply available before GPRSense, because only ground sensors were used, while now we do have really continuous maps of the root zone soil moisture. So I think this is really a major step forward to support precision irrigations. And so in terms of the instrument itself, the most exciting outcomes was to see that it works very reliably and provides really consistent results across the sites that actually we use from two different projects, the Duratec Farm project, a project at the University together with Agricultural Research Center in Belgium, and also during our collaborations with Osiris Agriculture with fields that were tested in France. And so actually the results were really exciting and demonstrated really the usefulness of such an instrument.
Sébastien, thank you so much for everything that you've shared and for being part of the Icaerus podcast series.
So thank you very much for the interview. I would just like to thank again the Icaerus consortium for the support through that GPRSense project. It really enabled a major step forward in developing and also bridging actually GPRSense to real world use. So thank you very much.
For those watching or listening, this episode is part of the Icaerus podcast series, where we look at how drones are being assessed and used in real agricultural and rural contexts across Europe. More episodes are already available, with new ones coming soon. Follow Icaerus on social media or visit the website to stay informed.